Hello, welcome to a tutorial on periodicity presented by the SHRDB with reference Cambridge International AS Chemistry by Laurie Ryan and Roger Norris. This is a tutorial on periodicity, and in this tutorial the learning outcome goes as follows. We have described and explained qualitatively and indicate the periodicity in the variation in atomic radius, the ionic radius, the first ionization energy, the melting point, and electrical conductivity of elements. Explain the properties of ceramic. Describe the reaction, if any, of elements of with oxygen and chlorine. State and explain the variation oxidation number and of oxides of sodium to sulfur and chloride. You have described and explained the acid-base behavior of oxides and hydroxides. You have suggested the types of chemical bonding and structure present in chlorides and oxides from their properties, and predict the characteristic property of an element in a given group, and deduce the properties of positions in periodicity table. So all these are what you have to visualize in periodicity. So now let's see the structure of the periodicity table. You need to know that the structure of the periodicity table is going to be arranged in order of atomic number. So we need to know that the periodicity table is made up of groups and we have period. But groups are meaning that when you say group, it meaning that you have the same number of electrons in its outermost shell, while the periods have the electrons all within the same shell. So that's the difference. And within the period, you need to know that there is an increase in atomic number, that is the increase in electronuclear attractions. So we have this is why we are going to consider the physical property in the period with respect to the periodicity of the physical property. So now, what is a periodic pattern of atomic radii? So we need to know that our conventionally we are going to choose period 3 in order to explain all this phenomenon. So now so the first thing to point out is you need to know that across a period we need to know that the electrons are entering the same shells, because you have to know that the first ionization energy, that is the ionic radii, is coming when electrons are entering different shells. You need to know that across a period electron is entering the same shell, and since electron enters the same shell, you also have, in addition to that, an increase in number of protons. So the electronuclear attraction is going to increase. So thus across a period, the more you move across a period, the more you are going to have a smaller atomic radius, and the smaller atomic radius comes because of a greater electronuclear electronuclear attraction. So you see that across a period atomic radii is going to decrease. That's the first point. So now we have again the next point, which that's this is diagram. So the graph, we have atomic radii against atomic number is going to decrease across the period. So now the periodic ionic radii, we need to know that for ionic radii, from group 1 to group 4, group 1 to group 4 are said to be metallic. From group 1 to group 3 are said to be metallic, while from group 4 elements are said to be non-metallic, but they can exhibit some metallic characteristics and non-metallic characteristics, and so that's what they are called semiconductors. And as from group 6, group 5 to group 5 to group 7, they are non-metals. So you need to know that metal atoms are going to release their electrons to produce their ions, while non-metal atoms are going to gain electrons to produce their ion. This is why we are going to see normally for atomic radii there is a reduction, but for ionic radii, since the metal atoms are releasing electrons, you are going to see that there is a decrease in this, since they release electron and they have the same number of shells, and see that this one have a greater electronic interaction, so electronuclear interaction. Since it has a greater electronuclear interaction, see that there's a decrease in cationic radii in this direction. And then you see that as we move from some silicon and go up to phosphorus, here you are seeing that they are instead going to absorb electron. Since they absorb electron, what happens in this case now is that the electron now is going to enter another shell, making the ionic radii to be larger. This is why the anionic radii for these known metals are going to be large, and the more you move across the period, the more electronuclear interaction, thus the radius also decreases. So you have ionic radii. So the ionic radii can be shown with this graph. Then we have the pattern of electroconductivity. A pattern of electroconductivity depends on number one, the number of covalent bondings which have been formed, and number two, the crystal which is formed by the substance. So the intermolecular force formed by the substance. So we have to know this point. So example, we need to know that sodium magnesium. Sodium has one electron that is going to release to form sodium ion in a metallic bonding, while magnesium is going to have two electrons that is going to release to form a metallic bonding, while aluminum is going to have three electrons that is going to release to form. So we see that the conductivity of aluminum is going to be largest because it releases three electrons in the metallic bond. So silver now, it has this one. The problem with silver 4 ion is that though silver 4 ion is going to release 4 electrons, the problem is now that it is having covalent bonding. The crystals of silver ion are going to have covalent bonding. Since they have covalent bonding, electrons are going to be held in place in this covalent bond, and then they are not going to be free. This is why silicon has a lower electroconductivity. And similarly to the phosphorus ion and silver ion, you need that to know that for this molecule, they instead have van der Waals forces. They don't have metallic bonding that is going to hold them together. They have van der Waals forces, and since they have van der Waals forces, they don't have going to have any electric conduction. So that's the point. And now you need to know the periodicity of the first ionization energy. We have seen already the periodicity of first ionization energy when we spoke about the electronic configuration of an atom. So we need to know that what for sodium, the first ionization energy is going to be low, and then it's going to increase for magnesium. The reason why it increased for magnesium is that magnesium, you have a greater so magnesium, you have two electrons in the outermost shell in case of magnesium, and the electron enters the same shell, but you have you have an increase in electronuclear attraction because in increase of number of protons. Since you have increased electronuclear attraction, in this case magnesium, you see that you are going to release electron. So now the next one is aluminium. So you need to point the fact that aluminium has a lower first ionization energy. And this is because it has a lower first ionization energy because the electron which enters into the aluminum shell, this electron now enters in the p subshell, so it enters in p1. So this electron that was entering inside the magnesium was entering inside the s subshell, while the electron entering inside aluminum is going to enter the p subshell, and that p1, that piece of x or py or pz subshell are going to have only one electron, which is going to be unstable, and now it's going to easily move out. That's why you have a small decrease for in case of aluminum. Then we have silicon. You have that electron is also going to enter in the same p subshell, but you have an increased electronuclear attraction. This is why the first ionization energy is high. And next one is that that electron is also going to enter again the same p subshell, so that's making 3 electrons entering the same p subshell, and you have an increased electronuclear attraction. Now going to the case of chlorine, you realize that you are going to have a smaller. Going to the case of sulfur, you realize that you are going to have a smaller first ionization energy compared to phosphorus, and this is because you need to know that completely full p subshell or completely full subshell is more stable than a half full subshell, which is more stable than partially full subshell. And now in this case, you see that in phosphorus there were 3 p subshell there were 3 electrons in the p subshell, and we need to know that there is supposed to be 6 electrons in p subshell. So this is half full, and half full is more stable than a partially full in case of sulfur, where there is 4 electrons in the p subshell. So since it's 4 electrons, you see that the 4th electron is going to be unstable, compared to though there is an increase in electronuclear attraction. That is why there's going to be a slight decrease in first ionization energy from phosphorus to sulfur. Then to chlorine, you see that there is an increase because you are going to have an increase because though it's partially full, there is an increase in electronuclear attraction. And then argon, there's again an increase in electronuclear attraction. That's the point. So these are the different points involved here. So now let's visualize a reaction of elements in period 3 with oxygen. We need to do that sodium react easily. So sodium react vigorously when heated and placed in gas of oxygen. So this is how it's going to react vigorously, and it reacts with a yellow yellow flame. So that's the flame that sodium is going to react with. Then the next one, we have magnesium also react vigorously when heated with oxygen to form magnesium oxide. Aluminum metal is protected by aluminum oxide plate. So you need to know that aluminum is going to be, so the first reaction is going to produce aluminum oxide metal plate, metal layer, and that is going to protect, is going to prevent further combustion of aluminum. So silicon reacts slowly with oxygen to form silicon dioxide. It reacts only slowly. We have phosphorus react vigorously with oxygen. A yellow or white flame is seen. You are going to see a yellow or white flame, cloud of white phosphorus. So you have phosphorus as such reacting to produce phosphorus pentoxide. And then we have again the next one, phosphorus pentoxide. We have again the next one, sulfur powder once ignited burn gently with a blue flame. Sulfur burn with a blue flame in a gas of oxygen gas. Toxic fumes of sulfur dioxide gas is produced. So we have sulfur dioxide produced in this case, and we have sulfur dioxide. Further oxidation of sulfur dioxide give sulfur trioxide. Their systematic name I can give this and this with respect to your oxidation number. So sulfur dioxide binding, you can use a vanadium pentoxide catalyst. So now, what is the periodicity of chemical properties? So now we are involved in the periodicity of chemical properties. The first one was a reaction with oxygen. Now they had a reaction with magnesium. We need to know that when sodium metal is heated, then plunged in gas of chlorine, there is vigorous reaction of sodium plus chlorine to give sodium chloride. When magnesium also react vigorously to produce magnesium chloride and aluminum chloride. Silicon reacts slowly with chlorine in order to form silicon 4 chloride. And then phosphorus reacts slowly with excess chlorine to form phosphorus pentachloride. So sulfur do form chloride such as sulfur dichloride and disulfur dichloride, but you do not need to cover this for these cases. So the next one, we have reaction of sodium and magnesium with water. We need to know that what sodium react vigorously with cold water melting in a bowl molten metal. So it is going to react across the surface of water, and this is going to produce sodium hydroxide and hydrogen fumes. So by contrast, magnesium react only very slowly with cold water, taking several days to produce a test tube of hydrogen gas. So the solution form is very weakly alkaline, a pH of 11, while this one is a strong alkaline, that's a pH of 14, sodium hydroxide. Magnesium is a weak base. Magnesium ion is a weak base and forming only a solution with weak pH of 11. So now we have magnesium plus water is going to produce magnesium hydroxide and water, a slow reaction. When heated, magnesium does react vigorously. So when you heat it, so this is when it's cold. When it's heated, magnesium react vigorously. Magnesium plus water is going to produce magnesium oxide plus hydrogen. So now we have oxidation number of oxides. So in order to calculate oxidation number, show the formulae some common oxides of periodic 3. So we have effect of water of oxides. So in order to, you need to know that generally when you place water in oxide, is going to produce sodium hydroxide, and this magnesium oxide water is going to produce magnesium hydroxide. But you have different cases in case of aluminum and silicon, where they are mostly amphoteric hydroxides. So now we have magnesium hydroxide, magnesium oxide and magnesium hydroxide are commonly used as indigestion remedy. In case of magnesium oxide plus hydrochloric acid is going to produce magnesium chloride plus water. Magnesium hydroxide plus hydrochloric acid is going to produce magnesium chloride plus water similarly. So now we also have now aluminum oxide. Aluminum oxide is not going to dissolve in water to produce the hydroxide, because here they are both acidic and alkaline, that is amphoteric. So you can have aluminum oxide as reacting with acid, and it can also react with alkaline. They react with dilute acid, and it's going to sulfuric acid to produce aluminum sulfate plus water, salt and water only. And they can react with a hot considered alkaline. When they react with hot considered alkaline, they produce complex ion of aluminium tetrahydroxide, so aluminium tetrahydroxide. So this is sodium aluminum tetrahydroxide. So that's the pentoxide. That's the complex ion. So this is now in case of silicon, it's only for silicon dioxide, the oxide of silicon for group 4, it is only acidic. So it's only going to react with the sodium hydroxide to produce sodium silicate plus water. So this is a point that you have to put in mind. Then the next one we have the oxide of group 5, that is phosphorus pentoxide, is going to react in water to produce sulfuric acid, and for that of group 6 is going to react with water to produce sulfuric acid. So all these are acidic. So we have sodium oxide is basic, magnesium oxide is basic, aluminum is amphoteric, this is acidic, phosphorus pentoxide acidic, and then sulfur dioxide acidic. So we have relative melting point of this is high, relative melting is high, this one is very high, and the reason is because in order to know this melting point, you have to know the crystal lattice in which are being formed for different cases. In case of silicon dioxide, it's going to be very high because they form a giant molecular lattice. Giant molecular lattice is actually very stronger compared to a giant ionic lattice, because giant molecular lattice have covalent bonding between different atoms of the molecule of the substance. So here is going to be low and there is going to be low. We have electric conductivity, good. We have known because it's a giant molecular lattice. In a giant molecular lattice, all of the atoms are being connected by covalent bonds, so there is no electron which is being released in the the surrounding, so it's being released in the matrix of the metal of the compound. So you have chemical bonding, you have ionic. This is ionic with some degree of covalent character. This is why it is a high melting point, because ionic with some degree of covalent character is covalent. This one is covalent, though these two are covalent, they don't have a crystal lattice. So this is why they are van der Waals forces which are acting here. You have structure here is giant ionic, this is giant ionic plus giant covalent for this case. That's why they have a relative high melting point. You have giant covalent, we have simple molecular and simple molecular structure. So these are different cases involved here. So we have the chlorides now. For chlorides, you have seen the formula of chlorides for each. You have the oxidation number for each, so that you have to know. So these are the different points that you have to put in mind. So, and from here we've seen all the different things involved in periodicity. So say thank you for your kind attention. Please don't forget to like and subscribe for the channel. Thank you.